we're gonna continue where we left off. So up until now, we have the bit stream loaded. We've loaded some C code to blink LEDs using the switches. We've loaded some interrupt service routine. Now, I'm gonna give a brief overview of all the other labs in the I/O section before handing over to Danny, who's gonna start going into the MIPS core in depth. Okay, so we have a set of other labs. I'll just quickly run through them. There's a 7-segment display. As you can see on the Nexus 4 DDR board, there's a row of 8 7-segment displays. Okay, now 7 segments, they might look simple, but they use a tricky I/O pattern. Okay, so you have to run through a timer to just like loop through each LED to make it, because each 7-segment basically has 8 LEDs in it. So that's 8 7-segments, 8 times 8, 64 LEDs. So we don't use 64 wires. They're wired up in a common anode configuration. So there's a whole lab that steps through and explains what the 7-segment wiring is, how we write the Verilog module, and how the software works on it. Okay. Now the next one, there's a reaction timer. You add a millisecond counter to MIPSfpga. So we have the clock 50 megahertz, we have some counters, we loop through, so you can have a deterministic counter once you know exactly what you've written. Okay, so you can have a sense of measurement in the hardware. If you want to measure 1 second in hardware, you have to start with the reference. It's the 100 megahertz crystal reference, then you have the 50 megahertz PLL reference, then you know 32-bit counter, 32 bits, how much time it takes to roll over, then you can run some calculations and then say, okay, now I have 1 second. It's a bit hard to make 1 second in hardware, but there's a whole lab for this reaction timer as well. Okay. The next one, so if you purchase a buzzer, any buzzer, you can add it onto the GPIO and just make it buzz in a different way. So there's a whole lab for audio and hardware to produce a square wave on the beam or DC pin, memory map the number of microseconds, and connect the buzzer. So you can just like connect the buzzer and just have a lab that works with some external hardware interaction. Up until now, we've been using the onboard Nexus 4 DDR itself, 7 segments, LEDs, switches. But what if you want to add an external sensor? So the buzzer is one of the simplest ones after LED and switches. Okay. Now, yes. Thank you. So now the something more complicated than the buzzer is the SPI light sensor. Okay, so SPI, it's a 4-wire protocol, TX, RX, master select, chip select, and those things. So this light sensor, we don't have them for this workshop at the moment, but they can be purchased from Digilit's website. We have a whole lab specifically for the light sensor. So Verilog module for SPI, because you need memory mapped I/O connection. We have some software for SPI, how to like access, go back and forth and stuff like that. Now this is a standard format. So there are, there are other sensors as well provided by Digilit. So there's one for relays. There's a joystick. I think this one is probably a resistant, and like various other temperature in those sensors. Okay, so just to go back a bit, to describe the interface. So from the MIPSfpga master, these signals come out on this second PMOD header. You wire out the clock, data out, data input on the slave, and once this plugs in, you have a connection there. Okay. Oops. This is how it looks like. We plug in the light sensor on here. The lab itself, we have some displays on the 7-segment. If you wave your hand on top of the sensor, the display changes, and so the lab workshop just walks through the whole process. Okay. Other sensors. There's also a small SPI LCD lab, so you can connect a tiny alphanumeric LCD, display stuff on top of it, and it's the same memory map peripheral. And this is all part of part 2, the I/O. So how you just have more and more interfaces. There's also the DMA access. So up until now, we just had a simple memory map access, but you can also use a DMA engine to write a lot more data onto some peripherals. So there's also a lab that goes through the DMA engine and arbiter and those like that. DES encryption, it's a whole different peripheral to a standard DES encryption and integrated with the DMA engine. So as I mentioned earlier, as you proceed with the labs, they just start getting more and more complicated as you can. This is still outside the MIPSfpga core. Okay, so I think lab 13, yeah. So now I'm gonna show Vivado. We haven't looked at the RTL project up until now. So now we're gonna open the RTL project and see if what it looks like. So in your workshop folder, just follow me, because we have a hands-on session after a while. Danny's gonna do this, and then you'll get more familiar with this as well. But try to focus on the screen at the moment. So in lab 1 Vivado, we have an existing project. If we open it, sorry. Okay. All right. Can everybody see this? I'm going to try and reduce some clutter. It's not clutter, it's useful stuff, but for now, yeah, okay. So I just wanted to walk through the top module and cover the interface bits, and then Danny's going to go inside the core and explain a bit inside as well. So this is the top module. Okay, the input, is that visible? Somewhat. So I'll talk through. So from the top module, from the platform, the Nexus 4 DDR platform, we take the clock, 100 megahertz clock input signal. We take the reset, CPU reset push button. We take the other push button up, down, left, right as input signals. Then we have switches, LEDs. Then we have JTAG pins and the UART pin as well. We'll use UART later as separately. For up until now in the workshop, we focused on the switches and LEDs as well. So then this clock wizard, it basically instantiates the PLL, which takes from 100 megahertz to 50 megahertz PLL. Then we have the MFP_system. It's another wrapper module. This one basically instantiates the MIPS core, the EHB bus, and the EHB and wires them together. So if we open this in Vivado, step inside MFP_system, we have a module in the description. We have some wires. See the H ready, H response, EHB signals, H clock, H reset, H burst. So these are all EHB signals. Then we have the system interface signals, SI, ND interrupt, NMI, non-maskable reset, IPTI. So there are some. Once you start opening the Verilog, you see that it starts getting a lot more complicated very quickly. All of these signals are documented, and the MIPS core itself is very, very configurable. So for example, there are 3 interrupt modes. You can cascade an external interrupt controller, which is an external interrupt controller mode. You have a vectored interrupt controller mode where all the bits are a vector, and you have the simple interrupt controller mode, which we look. And these 3 are controlled by other signals. So this is just a small example of how there are a lot more signals that you can pass to the core, which will just enable or disable different features. We go a lot wires. Then M14K top. This is the core itself. Okay, so this instantiates the MIPS core. We pass all these signals. Some of them are instantiated to default above. Some are we wire the EJ tag signals here. User defined. Okay. Now another module we instantiate in the system is the AHB. So MFP_AHB bus with all the signals. If we look inside the AHB, so yeah, you'll see you have the UART receiver. Remember I mentioned we didn't that you can also load program code through the UART, and it's a small Verilog module instance. So this is part of the AHB wrapper. There's also SREC parser is something else. 1 second. Yeah, EMFP AHB itself. So you go further inside the AHB bus, then you start looking at the RAM, the program RAM. Where is it? Sorry. Oops. So these ones, yeah. So module 0 boot RAM. This instantiates a boot RAM, passes the bus clock, reset, address, data. We also have the second program RAM, the 256 kilobyte one. Then you have the GPIO module. Then you have the AHB decoder, AHB mux. So this is in terms of Verilog. We've been looking at all the signals in PowerPoint, and we provided a bit stream. I just wanted to give a rough kind of step through that this is how all the external interfaces look like in Verilog, just kind of showcase the top wrapper. Now so parts 1 and 2 were focused on how we can bring up the MIPS core. We need to wire it with a clock, we need to wire it with a reset, we need to wire some AHB peripherals, we need to wire the JTAG debugger. Using that, you have a platform which can run some code and you can start working with some software and everything. But a lot of professors and students, basically, they want to go, okay, so this is still like the same as any of the NIOS or Microblaze or FPGA vendor kind of processor. This is where we get to the exciting part of MIPSfpga, that you can basically click the top for the microactive core and just open it. You can click the CPU, you can click the core, iCache, Dcache, the pipeline. So you can just click and open all the Verilog source code. And it's not just Verilog source code. There's a set of labs that walk through it. Now at this point, I'm going to hand over to Danny, who has far more experience in depth in these labs, and walk you through the performance counter and the further core stuff. I think. Yeah.
Is there something in the code that is dedicated, is coupled to this specific device?
No, it's just the top wrapper. So we have other top wrappers for, I think, Basis 3, Altera. So basically the core is just Verilog. Okay. All the signals around it, 100 megahertz clock, push buttons, LEDs, those are the ones that you just need to wire up. And we have a porting guide if you have your own dev board in your lab for bigger FPGAs. A lot of people have ported it on much bigger, faster FPGAs, clock it ahead or put multiple, and smaller FPGAs as well. We have a few other wrappers as well. We conduct the workshops with our Nexus 4 DDR board, but in terms of, there's no restriction or anything. It's all pure Verilog code.
And let me mention that in version 2, we've also included VHDL versions of top-level modules. So the core is still Verilog, but the system modules are also in VHDL, which many universities use instead of Verilog. So many of the labs can also be done in VHDL.
Okay. Thank you.
Yes. So we're going to part 3, which goes inside the core. Okay, so we'll start. It contains labs 6 or 7 labs, from lab 13 to lab 19. So we'll start with lab 13, which is about performance counters. Okay, we'll make use of the performance counters available in Microactive, and we'll examine different simple codes, and we'll test their performance, CPI, and so forth. We'll also use performance counters in many other labs later for measuring things like catch misses, catch excesses, catch write backs, and so on. So the goal of this lab is to learn how to use the performance counters and use them in real programs. The structure of the lab is common to many other labs. We first explain theoretically all the concepts. Then we, in this case, we provide a skeleton code that the students can use to include their programs, the programs that they want to measure. So everything else is ready, everything around the code is ready. And finally, we propose several problems with increasing complexity that use the performance counters. as you know, performance counters allow us to test functionalities and find bottlenecks in a system. We can measure different microarchitectural events, such as cycles, instructions completed, data cache accesses and misses, and many others. And it's implemented inside the system control coprocessor of MicroActive. There are two performance counters available. We'll call them PC0 and PC1. Each of them has two registers associated, one for configuring the counter. So for example, we're going to configure the event that we want to measure, which there are many events. Here we only show 12 of them, but there are many more. We're mainly going to use cycles, instructions completed, and cache-related events in these labs. And there is also a second register in each performance counter, which is the counter itself, which accounts for the event that we've programmed in the control register. Okay? This is the skeleton code provided to the students. I'm not going into the macros that initialize and read the performance counters. Everything is explained in the document for the lab. Let me just say that this macro initializes the counter, so it programs the control register in order to tell the counter which event to measure. And this one, it resets the counter and starts counting. And this one reads the counter. So here you're going to place your program, the program you want to measure. Finally, the values that you've measured with the performance counter are shown through the 7-segment displays. Okay? With switches equal to 0, we show one of them. With switches equal to 1, we show the other one. Okay? We're going to show you one of the exercises proposed here. You're going to do it in your boards so you can understand it better. This is a program extracted from the book by Harris and Harris, second edition, Digital Design and Computer Architecture, which we try to keep all the time associated to the book through these labs. Okay? So we're going to examine not only MicroActive, but also the pipeline processor explained in that book, okay? Which is quite similar to MicroActive. That way students can see that the processor explained in the book is not so far from the real processor they are using in the lab. Okay? So this is a simple program. It makes 1,000 iterations. It contains 5 instructions in the loop, a conditional branch, and unconditional branch, and some arithmetic logic instructions. Okay? What we ask the students to do is, first, we ask them to study analytically for the processor in the book, the CPI of this program, and then study for MicroActive. For MicroActive, they will study analytically and also empirically by using the performance counters. Okay? So this is the processor in Harris and Harris' book, and this is the processor, and this is MicroActive. You cannot see it here, sorry for that, but you have the source code of the figure in the workshop materials. You can zoom into the figure and analyze it. But you can see that both processors have 5 stages. Some of them are the same. For example, the fetch stage, instruction fetch, is more or less the same in both processors. There is a decode stage followed by an execution stage, which in the processor in the book is split into different stages, while in MicroActive it's merged in a single one. Okay? The coding and the execution happens in just one cycle in MicroActive. Then there's a memory stage which accesses the data memory, which is also available in MicroActive. Then there's a stage which is particular to MicroActive, which is the alignment stage. This one is not present in the processor in the book. You align the data that you read in the previous stage. And finally, there is a write-back stage, as in the book, okay, where you write the results back to the register file. Yeah.
Again, the extra stage, the new stage, what's the name and what's called?
Alignment. For aligning, if you access a byte, for example, you may have to align it, so you perform that in this stage. Okay. There are other differences between both processors. For example, branches are handled differently. In the processor, in the book, includes a branch predictor. It's a very simple branch predictor. It's just predicted, not taken, always not taken, and in case it misses, it just goes through to the correct path. But in microactive, you probably know MIPS architecture has a delay slot. So a delay slot is present here, so branches are handled differently. Okay. And finally, obviously, the memory access is different because in the book it's assumed to be ideal. Instruction memory and data memory will never miss. We'll always provide the information in one cycle. Whereas in microactive, we have real memories. We have a first level cache and then its memory. So if we miss in the cache, we'll have to wait for some cycles. This will never happen in the processor in the book. But those are the main differences. For the rest, it's very similar. So the analytical study for the processor in the book, well, I'm not interested in that here. We're interested in microactive for this workshop. It will obtain a CPI of 1.4. Ideal CPI would be 1 for this processor. It's losing some time because of some dependencies that have to stall the processor and because of the taken branch. But I think that's it. Let's not go into more detail here. Analytical study for microactive. Well, we can easily see that in this program we have around 5,000 instructions. We have 1,000 iterations. Each of them has 5 instructions, so around 5,000 instructions. And how many cycles will it take to execute the code? Well, each instruction should take 1 cycle, except if we miss in the cache. But note that this loop will be in the cache from the second iteration on, so it will almost be negligible, the miss latency in this program. And also, after each branch or jump, we have the delay slot. So by default, the compiler will introduce an operation in the delay slot. Okay? So we have to count for 1 more cycle here and 1 more cycle here. So in total, it would be 7 cycles per iteration, so around 7,000 cycles per iteration. If we make the maths here, we obtain an, well, it's not done here, but it would be around 1.4, the CPI obtained by default, if we don't use the delay slot. Now the question is, could we fill the delay slot with useful instructions? What do you think? Could we make this code perform better? Here we have an instruction that we can perfectly execute in the delay slot with no problem. And here we have an instruction which is the loop index, which we can move to the delay slot with no problem. Okay? In that case, we'd be using the delay slot with a useful instruction, and we would not have no operation. So we have a perfect CPI of around 1. Okay? Except for the catch misses in the first iteration. That's it. That's the analytical study. Okay? Let's go with the empirical study, and for that I want you to execute in the board. I'll guide you on the process so that you don't get lost, but well, you could easily do it yourselves. It's similar to what we've done so far. We have to download this code to the processor and execute it, and everything is prepared to show the performance counter measurements. So let's open the core. You already have it downloaded in the board because it's exactly the same bit file, so you don't have to do anything there. You just open the CMD. Remember to always close GDB and OpenOCD when you're going to run a new program. In the scripts folder, Well, first of all, we have to edit the skeleton file. So you go into MIPSfpga workshop, labs, part 3, the core, performance counters, and there you have a folder called skeleton code. Go in there, and you have to edit main.c. If you open with Notepad, let me tell you quickly what's here. These are the macros for initializing and reading the performance counters. Just let me show you that here we're writing a 0 in the control register in the event field, which means that we're going to measure cycles. And here we're writing 1 in the other performance counter control register, which makes the performance counter to measure instructions completed. So we're measuring cycles and instructions. Later, we'll change these values for measuring other things, such as data catch misses, successes, and so on. And the macro for reading the counters, well, let's not go in detail now. So if you go down in this code, everybody has opened this code. You see that you have the macro for initializing, the macro for reading, and in the middle, you have to place your code. You can obtain the code you don't have the slides, but you have the document for the workshop in your in the workshop contents. You can copy this code there, from there. You have the Word, you should have the Word file here in workshop contents, workshop guide. From here you can obtain the code. Let me do it. You go down here, you go to lab 13. Here you can get your code. Okay, let's copy this code to this file. Everybody has done that. We save, and now we're going to measure that code. So we load MIPSfpga and the program is here. And you should obtain, I don't know if you can you read this? Yeah. You should obtain around 7,000 when switches are all 0. Is that correct? Do you have that? So this is you should obtain that value. This is the amount of cycles needed for executing that code. And if you change the rightmost switch to 1, you obtain the number of instructions, which is 7,000. We said it was 5,000. The reason is that the performance counters are also counting the no operations as an instruction. But these are really not instructions in our program, right? They are necessary due to the way we're handling the branches, but they are not part of our program. Okay? So we should subtract the no operations, which in this case are around 2,000. In that case, we have 5,000 instructions, 7,000 cycles, which is the CPI we obtained analytically. Okay? So as we said, in this program, we could move some instructions to the delay slot, so they are useful instructions and will improve the number of cycles. Okay. Specifically, we are moving this instruction to the delay slot of the branch of the conditional branch, and the loop index increment. We're moving it to the unconditional branch delay slot. Okay. So you can replace the previous program with this new one. and run again. Let me say that when you run this script, load MIPSfpga.bat, you're not only downloading the program but also compiling it. Okay? So any changes you've made, you're going to compile the program again. So you run again, and now you will observe that the number of cycles and number of instructions has been reduced to around 5,000. Now we're not having no operations, so the CPI we are obtaining is very close to ideal. Okay? Observe that it's not exact the number of instructions that we could compute in the analytical part. This is due to some instructions, some extra instructions introduced by the performance counters themselves. And also remember that we have some cycles of delay due to catch misses, okay, which we will analyze in later labs. Okay? But more or less, it's the value we would expect here. There are some other exercises proposed with other codes, with different hazards, different stalls. Just to show you an example, here we analyze a different program where we have a load instruction. Yeah.
Just one more question regarding the branch delay slots. What happens if I place another branch into the branch delay slot?
Yeah, I think that's forbidden by the architecture, I think.
Okay.
So after the load, note that in the pipeline we are using, you will have to stall for one cycle when you have a dependency here, because the load will bring the data in the memory stage, then it will align it, so the add instruction won't be able to use it until one cycle later. Okay? So we'll observe a stall here that we can measure again with the performance counters. Okay? And this is just another example of some other codes that are proposed in this exercise. Finally, let me show you the disassembled code. Probably some of you have already looked at it. In the skeleton code, if you edit this program.this and you look for main, you can see the disassembled code that the compiler is generating. Well, this part is the performance counter initialization. Then here you can see your program, right? And you can see that in this version, the optimized version, where we, by the way, I didn't mention that for including these instructions in the delay slot, we have to use this directive, no reorder, that tells the compiler not to reorder the code within these two directives. Okay? So here, it's not introducing no operations. In the previous case, we didn't use this directive, so the compiler by default was introducing no operations here. Okay? You could also examine other optimization options of the compiler and see that it will automatically find some instructions. It's also in the document for the lab. It will find some instructions to fill the delay slot with by its own, okay, with no need of the programmer doing that. Okay? So you can explore many different cases. So we were in the disassembled program where you can see your program and you see that no operations have been added here. Okay? If we examine the same code for the original program with no optimized, this one, I forgot to tell you that. So if we change again the program back to the previous version, and we compile, you can see that the compiler has introduced no operations after each branch and jump. Okay? Any question about this lab? Okay, that's all we have prepared for this.
what I'd like to do is to just put this activity in context. You know, why does Imagination do it? What's the purpose of the program? You've got a summary of this in the university. No, I'll use the slide, use the spacebar name. You've got a summary of this. We gave you an introduction to the university program brochure. This summarizes the points I'm going to make. Okay. You've all got my business card. You've got any questions, you can, you're welcome to drop me a line, and I've got PDF copies of any of these brochures if you want them. First of all, let's just say a little bit about Imagination. We've been in the news for some not the best reasons in the past year. I'm not going to go through that, but the company's had a turbulent time. But the thing I want to stress to you is that I expect that Imagination will be under new ownership within the next couple of months, and that is going to bring renewed investment. And this company has some things of enormous value. If you use an Apple iPhone or an iPad, you're using our GPU. We believe it's the best GPU in the business. It's certainly, provably, the lowest power consumption that's on the market today. We're involved in making software-defined radios, except we call them radio processor units. This is Wi-Fi, Bluetooth, C6 low pan, many of the wireless standards that you need today. We've got digital solutions to that which you can integrate with processors. And for the last, nearly 6 years now, we've owned MIPS, which is a company that has a long history. It's very well known. We've succeeded in turning around the MIPS business. I can tell you that last year, twice as many MIPS chips were shipped as the year we acquired the company, which I think was 2012. So we're making significant progress. And some of you may have seen that Mobileye, which is the leading company in driver guidance systems, the autonomous car is almost certainly going to be powered by Mobileye systems. They use MIPS processors. And most recently, MediaTek, which is the second largest company in the world in terms of making wireless chipsets. Now, those of you who've got a Chinese phone, for example, it's almost certainly a MediaTek chipset. They've just started to use a MIPS in the modem processor. It's not the apps processor, but the other big processor in a mobile phone is the one that makes the decisions on what standard is running, what band should we be switched to. The modem is a very complex function. That is MIPS powered in the latest generation MediaTek chipsets. So you can see, although the publicity in the world may be that every processor comes from a certain company in Cambridge, actually the reality isn't completely true. And I would commend MIPS to you as having great value in teaching. Why? Because of the history, the fact that lots of you already know it, and that it's covered by the most brilliant textbooks. And in MIPSfpga, we're the only company to have shared our intellectual property openly with academia. No other company is doing what we're doing here, is to actually give you a core, the same core that our biggest customers pay a lot of money for. And by the way, those customers are strongly supportive of this because it means it's easier for them to design in their products. It's easier for them to find engineers who know how their products work. So that's the background to the company. We're an IP company. I think we have a bright future, and I'm very optimistic about what will happen to us in the next year or so. And we're based around three businesses: radio processors, GPUs, and MIPS CPUs. So why do we have a university program? Well, I've been doing university programs for many years. I worked for ARM, I've worked for Texas Instruments, I've done work for RS Components, and in all cases that there are really two objectives you have to satisfy to run a good university program. One is you've got to convince the teachers yourselves that we've got something useful that's worth using in the classroom. And then secondly, in those using those things, you need to create future demand for the products. So there's a good reason to have a university program. We would like your students to graduate knowing what a MIPS processor is and feeling comfortable to program it. And they may create future business for us. So there's a good commercial reason to have a university program. But let me stress that what we do has to be very respectful of your unique needs. So you may notice that our approach is very much an academic one. The kind of materials you're seeing today are written in the way a teacher would write the materials. That's deliberate. We mustn't turn the classroom into a marketplace. We have to respect that what you want are useful teaching materials and resources. The fact that they may help our business in the future is the justification for us to invest, but it is not an excuse to behave in a commercial way in the classroom. And I've been doing this over 20 years, and those that know me well, I think, would say that I'm a good custodian of your and respecter of your needs. So genuinely useful materials are the key to this, and I'm hoping that you're looking at the materials today and thinking, hey, there's some really good stuff here, I can use it. Those materials, they're free of charge for academia, they're very easy to get hold of, I'll show you how to do that in a moment, and they're provided to you in source code form. So we don't just provide videos and PDFs, but you can get access to the PPTs and the docs. So if you want to cut and paste, please do. One lecturer said to me, I love your materials, but it's embarrassing to have the imagination logo on there. And I said, fine, take it off, put your logo on. Oh, I can do that? And I said, for sure. I said, if you're using the materials with your students, we're very happy. And I don't mind if you decommercialize them by removing a logo. So please, consider these materials a pool of resources that you can reuse. If you decide to republish them in a book and use large amounts of them in a book, I'd be grateful if you'd contact me first so that I'm aware that the book is coming. We will give you permission to do that, and we'll help you promote it when your book appears. But just letting us know in advance would be nice. And we like to give good support, and you'll see that particularly for MIPSfpga, there's a really good forum running online now. There's about 150 posts in the library, and many of the FAQs around using this technology are now well documented. You know, 2 years in, MIPSfpga 2 is showing a level of maturity. We've managed to, I think, remove many of the most obvious catches and make it easier to get started. And you've been very smart. Coming to this workshop gets you over that hurdle of, you know, I heard a question earlier on was, is it working? And Zubair quickly looks at, there you are, it's running. You know, just knowing what success looks like saves a lot of time. There are 4 things that must be part of a good teaching package. And I've been responsible for teaching material development at several different companies. And you know what? I still come across companies who just don't get this. They just don't understand. But these are the 4 tests. The first thing is, whatever hardware you choose needs to be at a reasonable price. You know, I know expensive hardware can be really nice, but if you've got a classroom of 20 workstations, or in China, for example, where they may have 50 or 100 workstations, if the boards are too expensive, you simply can't use them in the classroom. So it depends where you are in the world, but the boards need to be, I don't know, $100, $200 a set per workstation. So you've got to choose something that's got the right features, that's robust enough. And for example, this is a problem with microcontrollers these days. Some of the microcontroller boards, let me give you an example, the ST Discovery board. It is a very, very cheap board. I think it's $14. The problem is that it's very easily broken, and it's very tiny, so the students can take it away in their pockets. And there's been 1 or 2 bugs with the drivers and so on. That's, in a way, that's too cheap for a lab platform. You need something that's more robust and better supported. So choosing the right lab platform is important. Robust enough, well supported, and that's why we have a partnership with Digilent. Digilent make really excellent teaching tools, and we've got quite close to this company. They've been very helpful to us, and we can strongly recommend their tools. They're not the only choice, but they're certainly a choice that I think you would find a safe choice. The second thing is software. This must drive you nuts. The number of companies that offer software with time limits. There are a number doing that now, one in particular that's very famous, and their software is time limited. What that means is that your students will probably hit that time limit the night before their project demo or something like that. It's a nightmare. Time limits are bad news. So some companies came up with an alternative. They put code size limits. We've all come across those. And in a way, they're even meaner, because a code size limit means just as the students are getting really good and they put in this excellent new feature, the software stops working. And to purchase software and license it is an absolute pain for every one of you. I know it. Even if the software is only $10, the fact you've got to pay the fee, put in a code, for when you've got tens of students, that's a pain. So I have a very simple philosophy. The software should be free. As simple as that. And the great advantage with the free software is it doesn't just save you money and time, but it means the students can set up and work at home if they want to. And the pocket lab, as I call it, the student starting off in the university and then taking some work home and continuing to work on it, it's a very powerful learning aid. So all the things that we will mention in the university program use free software, which you and your students can obtain in the full versions without any time or code restrictions. Third thing is support. These days, usually that's an online forum, and I personally monitor the forums for the Connected Microcontroller Lab and for MIPSfpga. And I think in the last 100 or so questions, I think there was one where we had to say, look, actually, I don't think we're going to be able to answer this one. But we've managed to answer all the others. And of course, quite often the users answer the questions before we do. And then there's the teaching materials. And for imagination, the creation of teaching materials means commissioning teachers to create those materials. We don't believe you can create those materials in-house. Now, several companies do their own teaching material development in-house, but the problem with that is that I don't think the materials are sufficiently exposed to student testing and student mentality before they're released, and the style and content of them is often too commercial. So I have a simple rule: all our teaching materials are commissioned externally, and we fund teachers to do that. That takes longer, it's harder work, but the end result are much better sets of materials. And when you look at the materials for MIPSfpga, there's not just a getting started guide, but in there are all the bits of code, the wrappers, the core itself, all the other things that you need. And that guide is written very much from a teacher's perspective. And then when you look at the labs, there's a student manual, there's an instructor's guide, there's test materials, there's solutions. It's not just a set of slides. And of course, some commercial companies, they will issue a set of slides and they think, there you are, go away and teach that. I'm afraid that's not the complete story. So fully featured teaching materials written by academics for academic use is really important. There are 3 packages that we support, which I'll cover in a moment. Let me just talk a little bit about some supporting projects we have. We strongly promote this book. We think this is the sort of practical guide that goes with Patterson and Hennessy. Harris and Harris, 2nd edition, is about digital logic. It starts off with the building blocks, it then looks at microarchitectures, and then it does what so many people do in their introduction to computer architecture. They build a simple MIPS. It then looks specifically at the PIC32, which is microchips implementation, and then logically, MIPSfpga is a way of going in depth into a commercial core. So this is very much the textbook that goes with this course. It also sits very nicely with our Connected Microcontroller Lab course. Let me warn you that there's an earlier edition of this. The 1st edition was also MIPS based, but is not as up to date. It doesn't include the PIC32 chapter. And there is a 3rd edition now called the ARM edition. That obviously is not based on MIPS, and it uses a Raspberry Pi. And in my opinion, and obviously I'm biased, but that book is far less educational on the subject of computer architecture than the 2nd edition. And the 2nd edition continues to be the top-selling issue of this book. We've been able to promote it and stimulate it to appear in multiple languages. It's available in Chinese, Korean, and in fact the Japanese edition of the second edition comes out next week, 11th of September. It's published. And we're offering free downloads of translations of this book in Russian and Portuguese. They're online from our website. So very, very important book. And we've produced a number of other supporting development tools and boards, which actually I'm not going to go into today, but there are details on the website. All our support is channeled through the website. Some of you I know have been up late getting ready for this workshop, and you've clicked the button to download materials, and then you've been waiting, when am I going to get the authorization to download the materials? And it's probably then that you've realized, oh, this is not an automatic system. You know, when you type in, I accept the license and this is what I want to do with the materials, it comes to me. And depending whether I'm online around the time or sleeping, you may have got a quick or a slow answer. But each one of those requests are manually answered. So do try and give us a little bit of time. And the reason for that is that we like to know who's using the materials and have some idea of what they're doing with them. I also am required to police that the license for these materials is for academic use. So when we give you that core, it needs to be for academic use. And as Zubair explained, basically inside the university you can do what you like with the core. The license agreement is very simple. There's a copy of it supplied with the materials. So if you want to go back later on and think, what did I agree to? It gives you the right to distribute the core and the materials to your students. So we've looked at it from the teacher's point of view, and we want to make it really easy. Being registered for the university program is important, because if you're registered, we're not going to spam you, but we will tell you when we have a workshop, when there's a new edition of the materials or any other special events. So that's the way we will keep in touch. And you must have an up-to-date registration in order to request these materials. Okay, let's have a quick look at the packages. There's 3 of them. There's one about graphics, which is written in OpenGLES 2.0. A lot of this is general graphics material. The hook to imagination, what brings it closer to our products, is that all the exercises run on a PowerVR GPU, and there's many different ways of accessing that. There's 10 different modules, go through some of the basics of graphics, and the author of these materials was a guy called Darren Mackay, who's at the University of Hull. He teaches gaming. That's his business. And if we take those 4 key tests that I mentioned earlier on, what about the hardware? Well, you can use an imagination platform, you can use some Android phones that have got our GPU. TI's BeagleBone or BeagleBoard has got an imagination GPU. In China, the Cubitech 4 and Cubitech 5 both use our GPU. You can use an iPad, an iPhone, or indeed there's a simulator if you don't want to use any hardware at all. The development software for PowerVR is completely free of charge. It's a download from our website, and there's one version for everybody. So you and your students are getting exactly the same software that the developers get. So no time limits or charges there. There's a thriving forum for PowerVR, and the teaching materials, they were the first of its kind, and they're targeted at later stage bachelor's or master's level gaming students who need to know more about graphics and have some idea of the constraints of mobile. Second package, which is really the heart of our activity, is MIPSfpga. And I'm not going to go through this in detail because that's what you're doing today. I've reminded you just what a revolutionary step we took in releasing this core. It took me 7 months to persuade the company to do it. Now what's lovely is everybody accepts that it was a really smart thing to do. So I feel, even though I've lost most of my hair and gone grey in my career, I do feel I actually achieved something in my career by making this possible. And as you know, it fits on multiple platforms. The cheapest platform I've seen it used on is things like the Basis 3 from Digital, which I think is a $70 platform. There's also a Thoracic D0 Nano. I've seen it ported on that. So it'll run on some very low cost platforms. If you want to do the SoC, which is the stuff that Zubair wrote, where you run Linux on the device, you need some extra space for your interrupt controller, your memory controller, and your peripherals, which is where a Nexus 4 DDR is a better platform because it's got a lot more space on it. So there's 3 sets of materials: a getting started guide, which includes all the extra pieces you need, as well as the documentation that takes you through it. There's the collection of labs, which is now 25 modules long, and then there's a paper specifically about SoC. We see this very much as a postgraduate course. Those 4 key tests, you know, low and medium priced hardware, and it's robust, so we meet that test. All the software is available free of charge, whether it's Codescape for programming the MIPS, or Vivado, the web edition, for controlling the FPGA, and we use OpenOCD for debug. So there are no charges or licenses involved there. We have a thriving forum now for MIPSfpga, and if you have a look at that, go on the Imagination site, click on forums, click on MIPS, click on MIPSfpga, you'll see lots of good stuff. It's always worth, if you've got a problem, it's always worth searching that. And in terms of teaching materials, Sarah Harris is the chair of the team that put the materials together. MIPSfpga 2, some of the labs have been contributed directly by Danny, who's here with us today, and we have a lovely team that work on these materials. And it's available, the materials are available currently in 5 different languages, including Chinese and Spanish and Japanese. So I think that covers several of the people here today. There's some material online. We will post the video from this online. And the plan is, when the workshop has been more polished, as I mentioned, you know, you are the first ones to do this. When it's more polished, we will record some studio-based tutorials, really professional tutorials with Sarah Harris that we'll put online. But we'll get to that later in the year. And the target courses, well, you know what they are: computer architecture, embedded systems, and for those who really want to go into Brave New World, system on chip. Now, some of these activities trigger interest amongst researchers. Some are motivated to modify the core, which you're able to do. And of course, a question that came up several times was, well, actually I rather like this MIPSfpga, but a soft core is not really what I want. I want to end up with a piece of silicon with a MIPS inside. And so to respond to that, we reached agreement with Europractice, and Mark Willoughby is here, sitting in the back corner there. He knows all about this. Europractice have a recommended design flow that you can use if you want to turn this into silicon, and Europractice can offer you a license at a very reasonable price that allows you to pick up the parent of this core. So the microactive you're using today has been ready configured. It's a standard configuration, by the way, not an educational one, so it is fully verified, but you can actually get the parent of this, which means you can do your own configuration and for example, include things like hardware virtualization, which might be important if you're working in security conscious environments. So Europractice can license you to get access to the core. In other parts of the world outside of Europe and Russia, that activity is handled by MOSIS. So if you're in China, for example, and you want to access this, then MOSIS in Shanghai can do the same sort of thing. So think about that a moment. You know, famous Patterson and Hennessy, there's the Bible. That's the theory of a MIPS. We've got a soft core, it's free of charge, you can all work with it. And for a modest charge, you can also license a core and make up to 100 pieces of silicon. We have the whole spectrum from concept to implementation in silicon. No other company can claim that. Okay, the third package is called Connected Microcontroller Lab. And this is all about the basics of microcontrollers. And we have a simple philosophy on this, is that quite a few universities, and I'm probably going to embarrass a few people now, are still teaching undergraduates on things like 16-bit MSP430s or 8-bit 8051s. Well, I got news for you. Most of your students, if they work with microcontrollers, will be working with 32-bit microcontrollers. In fact, something like 90% of new designs today, notice I'm saying designs, I'm not talking volume. There's a huge volume on 8-bit parts, but it's in a small number of companies. the mass market for microcontrollers has gone 32-bit. 32-bit microcontrollers are already the most common by far. So why not teach the students on 32-bit from the beginning? That's what this course is about. Basically, we're saying, hey, 32-bit is powerful, development time is quicker, the tools are better, there's a huge choice of parts, and of course, they support internet connectivity so much better. So we believe that undergraduates really should start with a 32-bit microcontroller, and the days of the 8051 finally should be brought to a close. And that's what this course is about. It begins with the basics, what's a microcontroller, and across a semester, across 15 modules, it takes the students just deep enough, not too deep, but just deep enough to understand all the things they need to do. They do the hello world, they learn to get data in and out, how to read the A to D converter. And at the end of it, they connect the system to the internet. And on their mobile phones, they can then read data from a remote node. So the Connected Microcontroller Lab is a start here, state-of-the-art, modern microcontroller course, and it's based on the PIC32. So just think for a moment. A student that does this course in their first or second semester, they'll be programming a PIC32. If later on in their course they do a computer architecture course based on MIPSfpga, at that point they'll go, I know this instruction set. Yeah, it's the same core. So there's a commonality between these two packages. This is complete. We've just posted some slight modifications. We corrected one or two little bugs, but it's a really smart, smooth set of materials. And this morning I had an email from a university in Israel who've just adopted this course. They're actually the third university there to adopt it. So we're very proud of it, and there are excellent tutorials online. There is a one-day workshop of this as well, and we've published the tutorials from the workshop from that. So it's very easy to get started with this. And it's a partnership. It's our core in a PIC32 on a digital platform. Notice, we chose a really robust platform. We didn't go ultra cheap. What we wanted was something that was reliable and robust, that would last for several years in a lab. And those tests, the hardware is about $100 a set, including the debugger. Software, it's the microchips MP Lab development environment for this package. It runs on 32 and 64-bit Windows, Linux and Mac. Typical microchip, makes it easy, covers everything. There's a good forum for this. Actually, that's a misprint. That should say Connected MCU. And full set of materials written in this case by Alex Dean, who's a professor at North Carolina State. He's written books on many different microcontrollers, and he teaches microcontrollers every day. So he really knows this subject. When you watch his tutorials, he's got that lovely, steady style of a teacher who really knows what he's talking about. These are just some snapshots of boards that are available that have got MIPS on them today. Something that a lot of people have been having fun with is the Onion Omega board. It's MIPS based, it runs Linux OpenWRT. They've had a lot of success. It was a Kickstarter project, I think, originally. They've been shipping lots of those. These are just some of the companies that we've been working with. And this is an example of a kit that Imagination put together. It's a professional IoT developer's kit. It's got a hub in it with a CI40, we call it the CI40 board. It's got an interactive based MIPS as a hub, and there's a pair of nodes that use PIC32s, and there's some samples of actuators and sensors that you can connect. So you can very quickly put together an IoT system, and there's some 200 different versions of these boards available, so you can quickly expand if you're a professional developer. So, final slide. Key thing is, make sure you're registered for the university program. If you go to imgtech.com/university and click the button Join IUP, it will take you through the sequence. Don't forget to tick the little box, because it brings up a brief registration, and on the bottom it says, do you want to join the university program? And you tick that box, and then, to be honest with you, about another 7 or 8 fields open up. It's a bit tedious at first, but once you're registered, it then means you're able to request any of these materials. So please, make sure that you've joined the programme. And I noticed, I think the delegate here from Magdeburg I saw did his registration while, I see a copy of everyone, so thank you. You're a model student. Full marks to you. And please help us spread the word. You know, we're a small company doing some good stuff, but we rely on word of mouth. And you know, it's happened to me, well, I've had 3 conversations here at FPL which have been along the lines of, you know, when we offer a MIPS core openly for educational use. What, a real MIPS core? Yes, it's one that's used commercially. What? And can we modify it? Yes, you can. Oh, really? You know, sometimes there's a bit of disbelief. You know, we really are sharing our intellectual property with you. And there's a reason why we do that. I know that our competitors don't share their IP, and that's their choice. They're very successful companies. Maybe they don't need to. But it's never been a secret how to make a MIPS. And lots of people make their own designs of MIPS-like processors. So why not give you a real one to have as a reference? It's logical to do. So we've come from a different place, and I think we've now moved to a very good place. I just wish we'd done it a lot sooner. So my thanks once again for all of you attending. I'll be around through lunch if you have any specific things you want to discuss, but please make the most of today, and thanks once again.